We live in a world of three dimensions. We can move forward and backward. That's one dimension. We can move left and right. That's a second. And we can move up and down. That's the third. We learn this so early it feels like a basic law of reality. A box has length, width, and height. A location on a map has a latitude, a longitude, and an altitude. It seems simple. It seems complete. But what if it isn't? What if the three dimensions we experience are just a slice of a much larger, more complex reality? Could there be a fourth spatial dimension, a fifth, or even more? This isn't just a question for science fiction. It's a serious idea that physicists have been exploring for over a century. It's not a wild guess. It comes from a deep problem at the heart of physics, a puzzle that suggests our familiar three-dimensional space might be an illusion, or at least not the whole story. To understand why scientists are even considering this, we first need to get a better handle on what a dimension actually is. Let's start from the bottom. Imagine a single point. It has no size, it has no length, no width, no height. It's just a location. This is a zero-dimensional world. You can't move anywhere. You are just there. It's not a very interesting place to be. Now imagine taking that point and stretching it out. You create a line. A line has one dimension length. If you are a tiny creature living on this line, you have only two ways to move. You can go forward or backward along the line. There is no left or right. There is no up or down. Your entire universe is that single line. This is a one-dimensional world. Let's take that line and stretch it out sideways perpendicular to its length. Now you have a flat surface, like a sheet of paper. Like this is a two-dimensional world. So it has length and width. A creature living here, a flatlander, can move forward and backward and also left and right. They can explore a whole plane, they can draw squares and circles, their world has area. But they have no concept of up or down. That direction simply doesn't exist for them. The idea of Flatland is a powerful tool. Imagine you, a three-dimensional being, decided to visit Flatland. You couldn't just step into their world. Your entire 3D body wouldn't fit. Instead, you could pass through it. What would the Flatlanders see? If you slowly lowered your finger through their flat world, they wouldn't see a finger. First, a tiny point would appear out of nowhere. As your finger moved through, that point would grow into a small circle. The circle would change shape as the cross-section of your finger changed. Then, as your finger passed completely through, the circle would shrink back to a point and then vanish. To the Flatlanders, this would be bizarre. An object appeared from nothing, changed its shape in a weird way, and then disappeared into nothing. They might call it magic, or a miracle. They wouldn't be able to grasp that it was just a slice of a higher dimensional object, you, passing through their reality. They are trapped in their two dimensions, so they can only perceive the 2D cross-section of 3D things. Now, we get to us. We live in a three-dimensional world. We take our 2D plane and stretch it in a new direction, one that is perpendicular to both length and width. We call it height. Now we have a space, a volume. We can have cubes and spheres. We can move forward, backward, left, right, and up, down. This is the world we know. So the logical next step is to ask, can we do that again? Can we take our entire three-dimensional space and stretch it out in some new fourth spatial dimension? A direction that is perpendicular to forward, perpendicular to left, and perpendicular to up, all at the same time. Our brains can't picture this. We are hardwired for three dimensions. We can't point in the direction of a fourth spatial dimension. But we can think about it using logic and math, and we can use our flatland analogy to understand what it might be like. Just as a 3D object is made of a stack of 2D slices, a 4D object, a hyper object would be made of a stack of 3D slices. If a four-dimensional sphere, a hypersphere, passed through our 3D world, what would we see? It would be just like what the Flatlanders saw. First, a tiny point would appear out of thin air. That point would grow into a small sphere. The sphere would get bigger and bigger to its maximum size. Then it would start shrinking, finally collapsing back to a point and then disappearing completely. For us, it would be a magical, physics-defying event, an object appearing from nowhere and vanishing. But for a 4D being, it would be as normal as a ball falling through the air. This is the central idea. We might be like the Flatlanders. We might be trapped in our three dimensions, only able to see the 3D shadows or slices of things that exist in a higher dimensional reality. The rules of our universe might seem strange to us only because we're not seeing the whole picture. And this brings us to the big why. Why go through all this mental gymnastics? Because some of the rules of our universe are strange. The main reason physicists are so interested in extra dimensions is to solve the biggest puzzle in modern physics: how to unite all the fundamental forces of nature. There are four fundamental forces that we know of. First, there's gravity. It's what holds the planets in orbit and keeps our feet on the ground. It's an attractive force that works over vast distances. Second, there's electromagnetism. This force governs electricity, magnetism, and light. It holds atoms together. It can be attractive or repulsive. It's much, much stronger than gravity. The tiny magnet on your fridge can overcome the gravitational pull of the entire planet Earth to hold up a piece of paper. That shows you how weak gravity is in comparison. Third and fourth are the two nuclear forces. The strong nuclear force is what binds protons and neutrons together in the nucleus of an atom. It's incredibly powerful, but only works over extremely short distances. The weak nuclear force is responsible for certain types of radioactive decay. For the last century, physicists have managed to describe electromagnetism, the strong force, and the weak force with a single, incredibly successful framework called the Standard Model. It uses the language of quantum mechanics. It's been tested and confirmed to stunning precision. But there's one force that stubbornly refuses to fit in gravity. Gravity is the odd one out. It's described by Einstein's theory of general relativity, a beautiful and powerful theory in its own right. But general relativity is not a quantum theory. When you try to combine it with the quantum rules of the Standard Model, the math breaks down. It gives you nonsensical answers, like infinities, and nobody understands why gravity is so mind-bogglingly weak compared to the other forces. It's like having 3 lions and a house cat and, trying to write a single set of rules that describes all of them. The house cat just doesn't seem to belong. This is the problem that keeps physicists up at night. They are searching for a theory of everything, a single framework that can unite all 4 forces and describe the entire universe, from the smallest subatomic particle to the largest galaxy cluster. And it was in the quest for this unified theory that the idea of extra dimensions made its first real comeback. In the 1920s, a little-known mathematician named Theodore Kaluza had a wild idea. At the time, only gravity and electromagnetism were well understood. Einstein had just described gravity as the curvature of 4-dimensional space-time, 3 of space, 1 of time. Kaluza wondered what would happen if he reran Einstein's equations, but with 1 extra dimension of space. A 5th dimension in total. He made a crucial assumption. He suggested that this 4th spatial dimension was not large and expansive like our own. Instead, it was tiny and curled up into a little circle. At every single point in our familiar 3D space, there is a tiny hidden loop of a 4th dimension, too small for us to ever see or notice. To picture this, think of a garden hose. From far away, it looks like a 1-dimensional line. You can only describe a point on it by saying how far along the line it is, but if you get very close, you see it has a 2nd dimension. An ant walking on the hose can not only walk along its length, but it can also walk around its circumference. The universe could be like that. We see the big, long dimensions, but we are too large to notice the tiny, curled-up one. When Kaluza worked through the math, something incredible happened. Out of Einstein's equations in 5 dimensions, he got back the original theory of gravity in 4 dimensions. But he also got something extra. A 2nd set of equations popped out, and these were almost perfectly the equations for electromagnetism. It was a stunning result. By adding 1 hidden dimension, he had seemingly united gravity and electromagnetism into a single theory. The 2 forces were just different aspects of geometry in a 5-dimensional world. It seemed too good to be true, and in some ways it was. The theory had some problems. It couldn't account for the other forces, which were not yet understood, and it made some incorrect predictions. For a while, the idea faded into the background, but it never completely went away. For decades later, as physicists were struggling with the problem of unifying all 4 forces, they came back to this core concept. The idea that the universe might have hidden, curled-up dimensions became the central feature of what is today the most famous and most controversial candidate for a theory of everything string theory. String theory starts with a radical new premise. It says that if you could zoom in on an electron or a photon or any other fundamental particle, you wouldn't find a tiny 0-dimensional point. Instead, you would find a tiny 1-dimensional string of energy, and these strings are vibrating. The key idea is that the way a string vibrates determines what kind of particle it appears to be. A string vibrating in one pattern would look to us like an electron. A different vibration pattern would look like a photon. Another pattern would be a quark. And crucially, one particular vibration pattern would have exactly the properties of the graviton, the hypothetical quantum particle of gravity. So in this picture, all the different particles and forces of nature are not separate things. They are all just different notes being played on the same fundamental string. It's an incredibly elegant and beautiful idea. It provides, for the first time, a framework where gravity and quantum mechanics can live together. But here's the catch. When physicists worked out the math of string theory, they found that it just doesn't work in our familiar three spatial dimensions. The equations become inconsistent and fall apart. For the math to be self-consistent, string theory requires the universe to have extra dimensions. How many? The most common versions of the theory require a total of 10 dimensions, 9 of space, and 1 of time. That means 6 extra spatial dimensions that we don't see. Where are they? Like in Kaluza's old theory, they are thought to be compactified or curled up into a tiny complex shape at every point in our space. But they aren't just simple circles. The math suggests these 6 extra dimensions are curled up into incredibly intricate, 6-dimensional geometric shapes known as Calabi-Yau manifolds. There are thousands of possible shapes these dimensions could take, and each different shape would result in a universe with slightly different physical laws. This is a mind-bending picture of reality. It means that at every point around you, in the air you're breathing, in the chair you're sitting on, inside the atoms of your own body, there is a tiny 6-dimensional labyrinth, a hidden geometric space that is simply too small for you to ever perceive directly. All the particles that make up you and your world are really tiny strings vibrating within this 10-dimensional space-time. The specific laws of physics we observe, like the mass of an electron or the strength of the forces, would be determined by the precise shape and size of those hidden dimensions. For many years, this was the dominant picture of how extra dimensions might work. They were tiny, microscopically small, so small that we would never be able to access them. But then, in the late 1990s, a new and even stranger idea emerged, also inspired by string theory. This is the idea of brane worlds. The name comes from the word membrane. The idea is that our entire three-dimensional universe might be a three-dimensional brane existing within a much larger, higher-dimensional space, often called the bulk. Think of it like this. Imagine a vast, dark swimming pool. This pool is the bulk, a space with maybe 4 or 5 or more spatial dimensions. Now, imagine a single, huge, flat sheet of plastic floating on the surface of the water. That sheet is our 3D brane. We, and all the matter and energy we know, are stuck to this sheet. According to this model, the particles of the standard model electrons, quarks, photons, are like open-ended strings. The ends of these strings are permanently stuck to our 3D brane. They can move around anywhere they want on the brane, but they can't leave it. They can't venture out into the higher dimensional bulk. This is why we only experience 3 dimensions. Our atoms, our bodies, our light, everything is confined to this membrane. But there is one exception: gravity. In string theory, the graviton is a closed loop of string. Because it has no open ends to get stuck, it is not confined to our brane. It is free to travel throughout the entire higher dimensional bulk. This provides a startling and elegant explanation for why gravity is so weak. The other forces, like electromagnetism, have their influence concentrated entirely within our 3D brane. But gravity's influence is leaking out into the extra dimensions. It's spreading its strength across a much larger volume of space. From our limited perspective on the brane, it appears incredibly diluted and weak. It's like shouting in a huge open field versus shouting in a small room. In the open field, your voice dissipates. What's really wild about this idea is that the extra dimensions don't have to be tiny and curled up. They could be huge. They could even be infinite. There could be another 3D brane, another universe, floating parallel to ours, just a millimeter away in the 4th dimension. We would never know. We couldn't see it or touch it, because the light and matter of that universe are stuck to its brane, just as ours are stuck to ours. But we might be able to feel it. The one force that can travel between the branes is gravity. The gravity from that other universe could leak across the bulk and affect our own. Some have even speculated that the mysterious dark matter, the invisible stuff that seems to make up most of the mass in the cosmos, could be ordinary matter on a nearby brane, whose gravity we can feel, but whose substance we can never touch. So we have 2 main ideas. The extra dimensions are either incredibly tiny and curled up, or they are large, and we are stuck on a 3D wall within them. Both ideas come from our best attempts to create a unified theory of physics. Both are mathematically plausible. But are they real? Is there any way we could ever find out? This is where science gets hard. It's one thing to have a beautiful mathematical idea, it's another thing to prove it. For an idea to be scientific, it has to be testable. It has to make predictions about the world that we can go out and check. If we can't test it, it's just philosophy. So how could we test for extra dimensions? There are a few ways physicists are trying. The most famous is with giant particle accelerators, like the Large Hadron Collider LHC at CERN in Switzerland. The LHC smashes protons together at nearly the speed of light. The goal is to concentrate enormous amounts of energy into a tiny point in space. According to Einstein's EMEC2, that energy can transform into mass, creating new exotic particles. If the brain world idea is correct, and there are large extra dimensions, the LHC might be able to create particles that are not stuck to our brain. When two protons collide with enough energy, they might create a graviton that flies off our brain and into the bulk of the extra dimensions. How would we see this? We wouldn't. The particle would simply vanish from our universe. But we would be able to detect its absence. In every particle collision, physicists carefully measure the energy and momentum of everything that flies out. These have to add up to the energy and momentum of what went in. It's a fundamental law of conservation. If a particle escaped into another dimension, it would look like energy and momentum had just disappeared. The collision would look unbalanced. This missing energy signature is one of the key things scientists at the LHC are looking for. So far, they haven't seen any conclusive evidence of it. Another way to look for extra dimensions is to test the force of gravity itself, but at very small distances. For centuries, we've known that gravity follows an inverse square law. If you double the distance between two objects, the force of gravity between them drops to 1/4 of its original strength. This law works incredibly well for planets and stars. But if there are extra dimensions, this law might change at very short distances. If two objects are extremely close together, closer than the size of the extra dimensions, gravity would not have had a chance to leak out yet. It would be concentrated and therefore much stronger than expected. The inverse square law would become an inverse cube law, or an inverse fourth power law, depending on how many extra dimensions there are. Physicists are conducting incredibly delicate experiments to measure the strength of gravity at the microscopic level. They use tiny plates and cantilevers placed just microns apart, trying to see if gravity behaves differently than Newton predicted. These experiments are fantastically difficult because gravity is so weak to begin with, and at those tiny scales, other forces like electromagnetism can easily interfere. So far, these experiments have confirmed the inverse square law down to a few tens of microns. No deviation has been found yet. This means that if there are large extra dimensions, they must be smaller than that. A third, newer window into this question comes from gravitational waves. These are ripples in the fabric of space-time created by cataclysmic events like the merging of two black holes. In 2015, we detected these waves for the first time, opening up a whole new way to observe the universe. If extra dimensions exist, they could affect how gravitational waves travel. Some theories predict that as gravitational waves ripple through space-time, some of their energy could leak into the extra dimensions. This might cause them to die down faster than expected, or it could create other stranger effects like extra modes of vibration that don't exist in standard 3D gravity. Scientists are now poring over the data from gravitational wave detectors, looking for any tiny anomaly that could be the first hint of physics beyond 3 dimensions. So, where does that leave us? We have this beautiful, compelling idea that our universe has more than 3 spatial dimensions. It's an idea that could solve the biggest mystery in physics, the unification of gravity with the other forces. It could explain why gravity is so weak. It could even hint at the existence of parallel universes right next to our own. But we have no proof, not a shred. Every experiment we have conducted, from the largest particle colliders to the most delicate tabletop measurements, has so far shown a universe that is perfectly consistent with having only 3 dimensions of space. This is the reality of science at the frontier. The ideas are often far ahead of our ability to test them. String theory, in particular, has been criticized for being untestable, at least with our current technology. The energies required to see the strings themselves are trillions of times higher than what the LHC can produce. The extra dimensions, if they are of the tiny, curled-up variety, are likely so small that we may never be able to build a machine powerful enough to probe them directly. So, could there be more than 3 dimensions of space? The honest answer is maybe. It's a real possibility. Many physicists believe it's not just possible, but likely. They see it as the most promising path toward a final, complete theory of the universe. The mathematics is too elegant, and the way it solves long-standing problems is too compelling to ignore. But a belief is not evidence. Science demands proof. For now, the extra dimensions remain a phantom. A beautiful, mathematically consistent ghost that haunts our theories of the cosmos. They might be the deepest truth about our reality, the hidden framework that explains everything. Or they might be one of the most elaborate and beautiful dead ends in the history of science. The search continues. We keep smashing particles, we keep measuring gravity, we keep listening to the whispers of gravitational waves from across the cosmos. We keep looking for a crack in our three-dimensional reality, a glimpse of the larger world that might lie beyond. Whether we find it or not, the quest itself pushes our understanding deeper. It forces us to question our most basic assumptions about the world we see, and to imagine a universe far stranger and more wonderful than we can perceive.